Hey everyone, I'm Jessica from Aspyre, and today I'll be taking you guys through part 1 of our Algebra and Functions unit, Relations and Functions. Today's math quote of the day is from Henri Poincaré, a French mathematician and theoretical physicist that made many important contributions to the fields of pure and applied mathematics. A fun fact is that in the 20th century, he formulated something called the Poincaré conjecture in topology, which was one of the most famous unsolved problems in math until it was finally solved in 2002 by Gregory Perelman. Poincaré says, mathematics is the art of giving the same name to different things. Starting off with the definition of relations and functions. Relations are a collection of ordered pairs or points x, y on the coordinate plane. Functions are a special type of relation that pair each x value with a single y value. Functions and relations can be described by various forms that include equations, graphs, sets, tables, and mapping. An example of an equation is y equals x squared minus 1, or f of x equals x squared minus 1. And the standard function notation is y equals f of x. On a side note, a handy trick for figuring out whether something is an equation or an expression is by looking at whether or not there is an equal sign. If there's an equal sign, it usually means it's an equation. If there isn't, for example, if we had x squared minus 1 instead of y equals x squared minus 1, we just have an expression. The most widely used notation when we express a function is f of x, but in reality, any letter can go here. And inside the parentheses goes the variable in the function, which is also usually x. And this is an example of a graph of a function, in this case a quadratic function. And these are more examples of sets, tables, and mappings. The domain is a set of values of the independent variable, often the x values, for which the function is defined. And this means that a y value exists for each value in the domain. The range is a set of corresponding values of the dependent variable, often the y values. In our first example here, we need to find the value of f of 2 when f of x equals x squared minus 3x plus 5. In order to find f of 2, we have to plug in x equals 2 into this function. And we get f of 2 equals 2 squared minus 3 times 2 plus 5 equals 3. For a second example, it's asking what the domain and range of the following relation is. So remembering how we defined domain and range in the previous slide, the domain is a collection of x values and the range is a collection of y values. In this case, since we have a set or a collection of coordinate pairs, the x values will be the first number in each pair. So the domain will be -2, -1, 0, and 1, and the range will be 3, 5, and 7. And we don't count this one because there's already a 5 over here, so it's not a unique value. Next, we'll be talking about the implied domain of basic functions. First, if f is defined by a function, the implied domain consists of all real numbers for which the function is defined. In a polynomial function, the domain is usually all real numbers, or from -infinity to infinity. For a rational function, let's say y equals 1 over x, the domain for this rational function is all real numbers except for x equals 0, because if x equals 0, that would mean we're dividing 1 by 0, which is impossible. Next, for radical functions, for example, y equals square root of x, the domain for the function y equals square root of x is all real numbers such that x is greater than or equal to 0. So that means non-negative integers, non-negative values, and that's because we cannot find the square root of a negative value. For our final example, we need to find the domain of the function f of x equals square root of 2x plus 1. This function is defined when 2x plus 1 is greater than or equal to 0, since the stuff inside the square roots cannot be negative, and that means the domain is all real numbers such that x is greater than or equal to -1 over 2. And we got this by using algebraic manipulation. Thank you for watching. We hope this helps. Next class we'll be moving on to part 2, which will involve linear functions. Goodbye.